effect of air pressure differences. Since the air above the cover page and beneath the cover page has differences, it will cause the effect we just mentioned. And this phenomenon inspired us to design the experiment to discuss with it. And here's the theory. We assume the volume of air under the cardboard be V of RT, and the volume flow rate will be written in this form. We take a derivative with respect to time. We can have this equation. And finally, we can have average radial fluid velocity be written in this form. And then we use the change in mechanical energy. We can have this equation, which K inside is the kinetic energy contained in the gap, and S out is the rate of energy flowing out the gap. And kinetic energy per unit volume can be written in this. And after integration, we can have this equation. K inside is equal to this. And then S out is the volume flow rate times kinetic energy per unit volume. So S out can be obtained. Since we have K inside and S out, we can have gamma air, the torque acting on the board due to the air. And we ignore the Bouillon force. We consider Newton's second law. We can have this equation. And gamma gravity is the torque acting on the board due to the gravity. And notice that we make an assumption if theta is approaching to 0. So gamma gravity is a constant here. And then after substitution into the Newton's second law, we can have this equation. It looks quite messy, so we let three dimensionless variables here be x, the scaling for theta, tau, the scaling for t, and the delta is the most important parameter since they are all dimensionless. So x, tau, they have no dimension, and delta is also no dimension, but you can see that I and theta, rho air, and La, they are all initial conditions of the whole system. So delta can represent the whole system, can represent the whole system. And after substitution into the equation, we can have this. This is the equation of motion. This is the equation of motion for our system, and delta is written like that. And we claim that the dynamics only depend on a single parameter delta. As long as we change the value of delta, we can have a different result. And if delta is the same, even though the plate looks exactly just different, we can have similar results under the scaled coordinate. And only when delta equals to 0, there exists an analytic solution, and it's written in x of tau is equal to cos to the power of -2. And when delta is not 0, there only exist numerical solutions.
And this is our experimental setup. And you can see that in this figure, the slide is shown by the motor through the transmission belt. And the setup can ensure the releasing time. So we can determine the initial angle of the cardboard. And you can see that in this figure, the cardboard is leaned against on the plate holder. And when we pull out the plate holder, the cardboard collapses. And we install NQ6050 sensor at the hinge of the cardboard. So it can record the whole motion of the cardboard during the releasing process. And this is our simulation. We choose three initial angles, 5, 10, 15 degrees. We get the following result. And these are some parameters for the simulation. So you can see that both figure A represents the angle simulation and both figure B represent the velocity simulation. And on the left-hand side, there are time versus angle theta and angular velocity omega. And on the right-hand side, they are scaled time tau versus scaled angle x and scaled angular velocity v. So we obtain this result. We find that when the initial angle increases, omega max increases as well, but v max decreases. And with the initial angle increases, the maximum velocity happens later. To get one data point, we have to repeat the following step for 10 times. First, we adjust the slider height to the initial angle of the cardboard. Then the sensor would measure the tilt angle of the cardboard, and then we pull out the holder to release the cardboard. Finally, the sensor would record the angular velocity of the cardboard during the whole process. And these are 6 plates that we use in the experiment. So you can see that this is our experimental results for the plate 1, and the horizontal axis is time and vertical axis angular velocity omega. So with the result, we find that when the initial angle is small, data fits with the simulation well. And second, with the initial angle increases, the omega max increases. And also, it happens later. Last but not least, when the initial angle is large, data cannot reach the expected maximum velocity. This is due to the theory we just discussed in the previous slide. It's under small angles.
And we transform the result we just have into the scale coordinate. The horizontal axis is scale time, tau, and the vertical axis is the scale velocity, v. The feature of this result is similar with the last result. When the initial angle is small, the data can fit with simulation very well. And when initial angle increase, the maximum speed of velocity will decay. And this is due to the scaling parameters, x, tau, and we call the square root, a. We can have this, v is equal to omega over initial angle times a. And initial angle times a, this multiplication will increase as long as initial angle increase. And due to this increasement, the Vmax velocity, maximum velocity will decay. And last, when initial angle increase, the moment when Vmax happen will be later. It will be postponed. And remember that we have 6 plates. We redo all the plates, and we can have this result. The horizontal axis is initial angle, and the vertical axis is the angular velocity, which will record the different plates for each plate and each initial angle. There are six curves in this figure, and which can represent a single plate in this result. And when initial angle is small, the data can fit with simulation. That's about like between the 10 to 15 at about 12 degrees. And when initial angle is large, the maximum velocity is lower than the simulation results. And last, we transform the data in the last page into this. There are 6 plates, and we transform it into scale coordinates. So in this figure, horizontal axis is delta, which can represent the initial conditions, like the width of the plate, length of the plate, initial angle, and air density will all be written in this delta. And in the vertical axis, Vmax will represent the maximum velocity for each data. And in this figure, most of the data can fit well with the simulation. When delta is small, some data here, they are above the simulation. And this might be due to the air loss at the short side of the board. And since there exists air loss, so the air cannot sufficiently support the board. So the board might drop it with a higher speed. So that higher speed will cause the data cannot fit with simulation very well here. And all the data will collapse into a single curve. We have 6 plates, but the 6 curves in the previous is in the unscaled coordinate. In here, they are all collapsed into a single curve. And we call that, in theory, we claim that the delta can suitably describe the whole system, and it's the only parameter that the whole dynamics will depend on. And here's the proof. They all collapse into a curve, and delta can well describe the whole system. And here's the summary. We designed and set up to ensure the initial angle of the height of initial angle of the board, and it is maintained. It is driven by a motor through a transmission belt to adjust the height of the board. And in theory, we have 2 equations of motions. They are discussed in the unscaled coordinate and scaled coordinate. In simulation and results, the result can fit well with the simulation when theta is approaching to 0. And when initial angle increases, omega max will rise while Vmax will decrease due to scaling parameters. And when initial angle is large, the data cannot fit with simulation very well, and both omega and V can't reach the predicted maximum value. And last, the data of all the plates will collapse into the single curve. And this is the proof that delta can well describe the whole system. And that's it.